and on the effect of attenuation in heterogeneous porous media is to discuss differences to metamaterials. So first I would like to show materials with inherent microresonators. I show one example with respect to metamaterials, and then I would like to discuss and show to you what I mean with natural materials. Afterwards, I discuss the effect on the micro scale. Micro scale in that context means that I discuss the characterization of one single oscillator from an experimental point of view, but afterwards I also show extended continuum-based modeling and numerical investigations. And last but not least, I would like to discuss the macro scale modeling. So everybody of you knows probably this spring mass system, an ordered system. That means that we have, let's say, the big mass points, the yellow things, the macroscopic springs, M1, K1, and the inherent oscillators with a certain stiffness and a certain mass. And the idea is that we have a periodic or ordered system, and when we investigate this kind of system, which is done, for instance, in the work of Liu or Huang recently, then we are able to calculate the effective mass as a function of frequency. And when we plot the effective mass, we got this characteristic result, which mean that we have on the one hand side, so this is a dimensionless result, that we have on the one hand side for the mass as function of frequency, we have a certain singularity around the eigenfrequency of the system. And when we look at the behavior of the in the low frequency domain, we have, let's say, an effective mass which is nothing more as the mass of the macroscopical system plus the mass of the microscopical resonator. When we go to the high frequency domain, then let's say in harmonic excitations, the mass of the microresonators are not observed anymore. So the effective mass is only given by the macroscopical mass. The interesting thing is now when we go from the high frequency to the singularity, then we observe a negative mass, so the results can be observed not that nice. So we observe then this negative mass effect, and this is quite controversially discussed in the literature. And there is, for instance, one statement which I like a lot, namely that says that in contrast to natural negative electric permeativity, no natural material has been found which possesses negative mass density or negative modulus. And this is mainly the motivation for me to show you one material where we exactly observe this kind of effect. So the question which is now arising, which I would like to answer, is how or do we observe such effects in natural materials like geomaterials? And with geomaterials I mean typical porous rocks, reservoir rocks, which we find, for instance, in hydrothermal reservoirs or in oil reservoirs. And if yes, how does the heterogeneity, which is completely different, of course, compared to such ordered systems, affects such properties like negative mass? So what we see on the right hand side is the typical distribution of the wetting phase in the pore space. So this yellow region here, that's the pore space, and this is saturated, let's say, with a wetting fluid. And what you are able to observe is that this is definitely not ordered anymore. Okay, let me come to residual saturated rocks. What do we understand? On the right, we see oil wetted sand. The gray particles here, the shaded particles, these are grains. And in the pore space of the grains, we have a continuous light phase. This could be, for instance, a gas phase. And we have this black phase, this menisci here. And this is, in that case, it's an oil phase. That's the wetting material. So from a mechanical point of view, from a modeling point of view, we have a discontinuous wetting phase. So these clusters here, these oil phases, they cannot connect. But the pore space which is filled with the gas phase is a continuous phase, and we assume that we also have that also the grains can share some contact forces, so we also have a continuous solid phase. So we have two continuous phases and one discontinuous phase, and I'm especially interested now in discussing with you the effect of the discontinuous phase. So this is more or less the picture which we later on will discuss in more detail. And in order to convince you that we are able to see such menisci also in natural materials and not only in sketches, I show you here X-ray synchrotron scan from a typical sandstone. In that sense, it's a German sandstone. That's a Bentheim sandstone, and this is water saturated and air saturated. And we see here, for instance, the gas phase, and here the water phase. So that's a raw image. That's why it looks not that nicely. And when we compare the image with the sketch on the left-hand side, then the phenomenon is quite similar. The nice thing with this sort of synchrotron-based X-ray tomography is that we are, for instance, able to characterize the contact angles by means of images, and this can be later on also used, for instance, to characterize the surface weathability of such kind of materials. Okay. What are things which we have to take into account into the model? As I already said, we have the discontinuous wetting phase, and in the discontinuous wetting phase we are not able to have some propagating information, so we have a no propagating wave in the discontinuous phase, no communication about these liquid clusters. But what happens now if we, let's say, if we perturb this discontinuous clusters by, for instance, an harmonic excitation, then they are oscillating somehow, they are displaced, so that means that we have a relative displacement between the solid skeleton and that kind of wetting phase, and in the most simple assumption, this is just an elastic response, so we have a non-dissipative mechanism, and this mechanism, of course, is on the micro scale. On the macro scale, we are then able to observe something which is very similar to that what we have observed when we discussed metamaterials, namely a peak in the intrinsic attenuation. This plot here shows the intrinsic attenuation over frequency, and the peak arises at the eigenfrequency of such kind of liquid clusters, and for, let's say, such relatively simple geometries which are sinusoidal shaped, we can do this analysis also analytically, and this was, for instance, done in the work of Marcus Hilbert. Okay, in order to convince you that this effect can be modeled with a very simple rheology, with an oscillator type rheology, we have performed some physical experiment, and the idea of the physical experiment is shown here on that sketch. So we have one crane, a second crane, and in between there is one liquid blob, one liquid cluster. Of course, we have surface tension effects which are dominated in that sense, and now we would like to perturb it a bit, and we would like to discuss the dynamics of that liquid cluster. Therefore, we put such a liquid cluster on a magnetic shaker. We excite it in the frequency domain, and what we see here when we use a specific liquid, a so-called test ink, which has a specific contact angle, and we clamp it in between, we see this typical movement in the first eigenmode. Of course, this can also be done by sweeping frequency, and then I show here the amplitude in the frequency domain, and what we observe is very similar to the rheology of a classical oscillator. So we see the peak corresponds to the first eigenfrequency, but we are also able to observe higher order modes, which corresponds then, of course, to higher order eigenmodes, and this can be, for instance, observed, as in that case, with high-speed cameras. Okay, so from now on, I would like to restrict myself to, let's say, to small perturbations, to linear dynamics. That's why I'm only interested here in the first eigenmode, and this is later on that what we also would like to put in on the microscale in a macroscopical model. Okay, in order to discuss this rheology in more detail in order to set up a numerical framework based on some theoretical models. On the micro scale, I would like to set up a finite element framework where we are able to model also more complex geometries, for instance, based on images which we got from tomography. And therefore, we have to think what kind of effects has to be taken into account in a model. Of course, we should take into account surface tension, which means on that scale that we have to take into account Young's equation, the Young-Laplace equation, and we have to extend the Navier-Stokes equation to take into account the surface tension effect. So this is the liquid cluster here, which is surrounded by the gas phase and by the solid phase, and in the interface we need boundary conditions for the Navier-Stokes equation, which takes into account surface tension. For a finite element model for small perturbations, it is more convenient to use, especially with respect to this boundary conditions, to use a total Lagrangian framework. And then let's say we would like to determine two states, namely we will start from an arbitrary state which is not in equilibrium. That means first we have to determine the equilibrium state, which could be something like that. And when we have that state, we would like to perturb that state and do a dynamical analysis, and from that dynamical analysis we would like to determine the first eigenmode. Okay, therefore, and this is very much motivated by Francesco, who told me 2 years ago that I have to be more variational. Therefore, I propose a variational approach where these sort of physical effects are implemented, namely the bulk properties. So you hear the internal and external virtual power of the bulk properties of the fluid. And in addition to that, we also implemented the virtual internal and external power of the interfaces and also of the contact lines. So we neglect here the effects of the contact points, which in principle also has to be taken into account. But with respect to dimensional analysis, we assume that these are of higher order. Okay, this is the framework, and exactly that what I have shown you here can be used in a finite element formulation in order to start, let's say, from that what I called arbitrary state to the second state, which is then an equilibrium state. So we use that to calculate equilibrium, and from that equilibrium, which is then perturbed, we do the dynamical analysis, and here the typical response in time domain is shown. And from this response in time domain, we can apply the Fourier transform and then obtain the first eigenmode. So this is the framework. And using that framework, we are now able to analyze certain liquid distributions, very simple ones, for instance the one here which is just a square with a given contact angle, with a given aspect ratio. This is the length, this is the, let's say, the width, and from, let's say, these dimensions we are able to calculate, for instance, the eigenfrequency but also damping, and when we take viscosity into account. And as you see here, we have done that for certain geometrical distributions, and you see, for instance, that the typical eigenfrequency which is obtained starts, roughly speaking, for a very, let's say, long liquid cluster in the order of 300 Hertz up to 10 or even 100 kilohertz, depending, of course, on the geometry. Okay, after we have modeled and tried to understood the behavior on the micro scale by means of experimental investigations and a numerical approach, we would like to use that information in order to enrich classical macroscopical models. And the classical macroscopical model to investigate wave propagation in porous materials saturated with a continuous fluid is Biot's poroelasticity. This has now to be extended by taking into account the effect of this liquid clusters. So, what is the basic idea now? We have a certain representative elementary volume. Here we have the distribution of the clusters. We know now the eigenfrequencies. They are somehow distributed, of course, in a representative way. And that means, from a rheological point of view, they behave like that. Here, in addition, let's say, to to the undamped oscillator we add a certain, let's say, damping phenomenon, and that damping phenomenon could arise, of course, from the intrinsic viscosity of the clusters, but especially from sliding motion between the cluster and the solid interface. So this is then in a phenomenological way captured in one, let's say, damper, in one dashpot. Of course, depending on the geometry and depending on the calculations which I have shown here, we are then able to set up the eigenfrequencies here, and we are able to calculate them. And these have now put in parallel to the classical continuous phases. I don't spend any word on explaining the continuous phases in details. That could be, let's say, to make, if one would like to only to discuss the effect of the discontinuous phases, this could also be, let's say, the classical wave equations of linear elasticity, right? But here, in order to be closer to a reality, we use the poroelastic approach. Okay, and these are then the resulting field equations which we got from these kind of investigations. Let me very briefly go into details of this kind of formulations we show here. These are the classical equations of BO, classical wave equations of BO. I only would like to go into detail into the momentum interaction which we show here with this head term on the right hand side. And typically we have here the interactions which are caused by viscous drag forces. So we have here these relative velocities which are driving, let's say, or which are responsible for the classical BO type of damping. And this, of course, also arises here in the field equation for the fluid phase. So these are standard, sorry. And on top of that, we have now, let's say, the series of oscillators, again, with a momentum interaction contribution, and this momentum interaction contribution takes into account the rheology of the oscillator, and this is shown for instance here. So we have the relative displacements now, and if we take into account sliding motion, we also have, let's say, an additional viscous damping effect. This can all be evaluated by assuming harmonic waves. The classical ansatz for the waves for the solution, and then we end up in an eigenvalue problem, and this eigenvalue problem can be solved. Of course, there are some steps in between, but they are quite standard, so I don't want to go into details. What we get then is a description which we can find, for instance, in that way in various contributions. I like the form which was presented, for instance, in the work of David Smulders. He wrote the solution down in these complex densities, and the classical classical solutions of BO are only, let's say, depending on these terms on the left-hand side, and the effect now of these internal resonators are captured by these both sums, right? They take into account this oscillator type of phenomenon, which now can be solved. So we can solve the dispersion relations, and if we think about that, what I have shown you at the beginning with respect, for instance, to these microtomographs, we have, of course, a certain distribution of that eigenmode, and that motivates us to replace these sums here by a simple distribution function. So we can also express the solution of the dispersion relation with respect to the distribution of the eigenmodes, and this is done here. And when we do that, when we solve that, we are also able to come back to what we have discussed at the beginning, namely the solution of an effective mass. Of course, now we are on the continuum level, so we are not able to calculate an effective mass, but we are able now to calculate an effective density of the representative elementary volume, and what we see is completely identical to that what we have discussed at the beginning with respect to metamaterials. We also see that we have a singularity when we only take into account one eigenmode, so all these oscillators have the same eigenfrequency, then we see completely the same effect. So also we have also a negative mass effect, so that's completely identical. But what happens now when we do not have in a representative elementary volume only one eigenfrequency, when we have a certain distribution, and this is shown here. not with respect to the effective mass, but with respect to the phase velocity and the damping, so the imaginary part of the solution here expressed by the so-called quality factor. And then we see a quite interesting phenomenon, namely when we have this ordered system, that means only one eigenmode, we have again the singularity in the phase velocity, and then we make the distribution wider, wider, and wider. Then let's say the singularity is smeared out, and we obtain a solution which is completely smooth on the one hand side, but shifts the frequency to the right hand side. That means from an interpretation that this ordering shifted the attenuation to higher frequencies. This is, let's say, the character of these damped oscillators, and probably also of interest, the shape of this dispersion curves are completely identical to the shapes which we know from the classical BO theory, but the characteristic frequencies is shifted 1 or 2 order of magnitudes to higher frequencies. More or less the same effect do we observe when we discuss attenuation. Of course, again, when we don't have any disordering, when we have an ordered system, all these oscillators have the same eigenfrequency, then we have the singularity, then we have a stop band, so to say, and when we take this order into account, then attenuation is on the one hand side shifted to the right to higher frequencies, on the other hand the frequency band where waves are attenuated are also wider, and the amount of attenuation, let's say, is getting lower. And this is again very similar to that what we know from classical BO type of materials. So let me very briefly conclude what we have observed, and this is let's say I would say a very nice diagram which can be found in the rock physics handbook. So where they tried in that handbook to characterize damping mechanism which can be found in typical porous rocks. Here, for instance, we have the classical BO phenomenon. The damping, the critical frequency, is characterized by the viscosity of the pore fluid and is characterized by the permeability. So if we increase, for instance, viscosity, then we also shift the characteristic frequency where damping occurs to higher frequencies. When we lower permeability, we shift the characteristic frequencies to the right hand side. But what is even more important is that the characteristic frequency is very high with respect to frequency, which is the 100 kilohertz regime, for instance, or even higher. What we have seen when we discussed the eigenfrequencies of oscillators for typical pore morphologies, pore shapes, then we have already discussed that we can come down, let's say, to 100 hertz or to 1 kilohertz. That means we have a non-classical damping mechanism in reservoir rocks which is much lower than that one of BO. And this is something which, when you talk with people from geophysics, for instance, which you also observe in experiments. So with, let's say, such a mechanism, of course, on the top of other mechanisms which also explain damping in the lower frequency domain, we have a further mechanism which also explains damping. And with that statement I would like to stop. Thanks.
Thank you very much. So we want to start the discussion. So can we really say that we have found now another geo-metamaterial?
I hope so.
Mark, look at this plate. There is you can find these rows and clusters.
I've already seen it, exactly. Then we can mobilize it.
Good. Yeah. Yes, very interesting. In case of geophysics, when you have two fluids, I assume that vibration should be much smaller than.
Exactly. That's a very good remark. When you have, for instance, oil and water, then of course oscillations are much lower. So this is especially an application which is more, let's say, which is important in shallow reservoirs, for instance, where you have a certain amount of gas phases, right? I think it's of non-importance when you have really oil and water.
Francesco?
Simply, if you remember, there was a talk by Carcadera, in which he conceived a trick with George-same equations to trap energy. Now the question is, do you know if in natural materials this happens or sometimes has been observed?
So I think it's very hard to answer very quickly. No, I don't know. And I think it's also very hard to interpret the data. This was a little bit the motivation of the dispersion relation for the disordered system, which I would like to discuss. Because what we see when we have a certain distribution, which we always have in disordered materials, then the shape of the dispersion curve is very similar to the shape, for instance, of the BO curve, right? So when you measure something like that, you have two possibilities. Either you say that's a BO material, a classical poroelastic material, and then you don't need that model, right? So that you explain with an established model the effects, which are probably of completely different nature, right? And for my part, I found it very interesting that on an effective scale, the observed mechanisms are quite different to that what you expect. So I think one has to think about, or one has to do some let's say some numerical simulations, for instance, which help a lot to understand the physics which are going on the micro scale.
Cool. So another question. Here the resonator is mostly the elastic effect is mostly due to the stiffness of the surface capillary.
Yes, exactly. It's driven by surface tension, exactly.
Is there any experiment with surfactant that change the frequency?
The surface tension. Yeah, of course, when you add some surfactants, for instance, you change a lot surface tension. That could be something which is of interest, of course, for the oil industry, right? When they would like to mobilize such kind of blobs, then normally they add some surfactants, right, in order to minimize surface tension. And then, of course, you have, by seismic stimulations, you can, for instance, mobilize such kind of liquids. Yeah, exactly. Mm.
Okay. That's one. Sorry. Yes. We have a question for us.
Does it work? Oh, okay, sorry.
As far as the role of evaporation, if you are under condition where you have low relative humidity, you may have a problem with physical stability of this liquid phase, so that essentially the mass balance of the liquid phase changes, and so the capillary force. So you may have a couple of problems. First of all, the nature of those meniscus change, and there is also some internal
Sure. Sure. So what I showed to you was one. Well, that's why I split, for instance, when I investigate the resonators on the micro scale, why I first calculate an equilibrium state and then I perturb the equilibrium state. So I assume that, let's say, when we discuss, for instance, waves, these are always very small. These oscillators are the amplitudes are very small, right? So I can start from a given equilibrium state. And then I don't take care about these effects anymore. Exactly, but these time effects.
Zero light may be okay, for instance, if you have some stable phase.
Exactly.
That's perfectly fine. That's not always the case.
Then you do have to take into account, but you always have to start from an equilibrium state. So this is linear wave. These are linear wave or linearized wave equations, right?